Okay, so now we're in a scenario where one of these two selection coefficients is greater than the other. They just can't be equal. One will be larger, one will be smaller. So what is that trying to do? Well, let's think about this again from a graphical viewpoint. Over time, if we look at the frequency of the A1 allele, or P, S, the selection coefficient, is trying to increase P, so it wants to get P up to a value of 1.0. T, on the other hand, is trying to fight it back, and it says, no, I don't want the A1 allele to win, I want the A2 allele to win. So it's going to try and bring P down to 0, where S is trying to bring it up to 1. So what you can see is that we have one force trying to increase the A1 allele, one force trying to decrease it. Those two lines are going to form across an intersection, and as we already talked about in class before, that makes an equilibrium. Now when we look at the situation where the heterozygote is advantageous, if you want to think of it, we have it in a different type of a fashion. It's just working in the opposite. We have time, and we have the frequency of the A1 allele. This time now, though, since S and T are both less than 0, that means S is negative, T is negative. So S is trying to decrease the frequency of the P allele, and T is trying to increase it. So we see the same thing, though. Two opposing forces, one trying to decrease the frequency of the A1 allele, another force trying to increase the frequency of the A1 allele. So we end up with an equilibrium. Now think back for a minute to when we were looking at mutation. And when we had two-way mutation, we saw the same type of patterns here. And when we tried to figure out what the equilibrium frequency of P was, it was what the relative strength of those two mutational pressures were. So we're going to see the same thing here. Our equilibrium value is going to be based upon the total amount of selection that we have in the system, which is S plus T, and then it's going to be relative to what our value for T is. So what does this mean for our graphical representations of what we were looking at before? I always come back to the graphical stuff because it seems easier to understand when you look at a graph than when you just try and do it mathematically. So let's take a look again at a situation where we're trying to figure out what our average fitness is in a population with respect to the A1 allele. And we're going to do it from both graphs that we were looking at, which is delta P relative to P, and the average fitness in the population relative to P. So we're assuming that S is greater than T. We don't care what it is, we just assume that it's going to be larger. So what should happen to our equilibrium points? Well, we know we still have equilibrium points when P is equal to 0.0 and 1.0. So we know we're going to have equilibrium points. That means delta P is not changing. Now, when we think about where those equilibrium points are, though, or what the average fitness of those populations are, since S is greater than T, when I only have A1 alleles, the average fitness is going to be 1 plus S. So we're going to plot that somewhere up here. Now, in contrast, if I only had A2 alleles, my average fitness in the population would be WQQ, which would be 1 plus T. But since S is greater than T, that must mean that 1 plus S is greater than 1 plus T. So I know that my value for W bar, when I have no P alleles, I only have Q alleles, has got to be somewhere below that point for what it is when I only have P alleles. So now you notice that the average fitness values are different whether I have only Q alleles or I have only P alleles, and it's greater when I only have P alleles. Now if you remember when we had S and T equal to each other, our equilibrium point was also 0.5. But now since we have them struggling against each other and they are not equal in strength, it doesn't end up always at a tie. Now which one should win? P should win. And well, if P is going to win, that means that we can start further to the left of 0.5 and still go to fixation. We expect our value, our other equilibrium point, to be somewhere to the left of 0.5 when S is greater than T. And we see a graph that looks something like this. So that means that our equilibrium point here is going to be less than 0.5. We'll still have delta P being negative for that portion and positive for that portion. So it seems kind of counterintuitive in that when S is greater than T, the equilibrium value moves to the left. Why that's the case though, and when you think about it this way, it might make more sense. Since S is greater than P, it essentially says that this genotype is better or stronger than this genotype. So if we think of it as a tug of war, we should be able to give the WQQ individuals a head start, let that flag be closer to their goal point, and WPP should still win. So there is more area that results in the fixation of P compared to the fixation of Q. If we look at it with an example, if we take S at 0.4, T at 0.2, we can see that our equilibrium value is going to be 0.2 divided by 0.4 plus 0.2, which equals 0.33. So that means my equilibrium value, my unstable equilibrium value, is now going to be at 0.33. As long as there's just over 33% of the alleles in the system are A1, I'm going to fix the best allele, the A1 allele. In contrast, if just under 33% of the P alleles, I'm going to fix the A2 allele. So what's going to happen then when we look at heterozygote advantage under this system? You might think that my P hat should still always be P equals 0.5, the equilibrium value, because that's where I get my most heterozygotes. The problem though is that you're also getting the maximum number of both types of homozygotes. Because remember, if I do a Punnett square for my heterozygote, 50% of my individuals are going to be homozygotes and 50% will be the heterozygotes. Let's see what happens to our P hat with our two graphs. This is W bar again, delta P, 0, and then down here I just have my P. Well, why don't we end up back at P equals Q equals 0.5? Well, if we think about it from the standpoint of what the whole system looks like, if P equals Q equals 0.5, that means 25% of my population is going to be PP and 25% of it is going to be QQ. But now, since S and T are not equal to each other, that means that one of these genotypes is worse than the other one. So by keeping my equilibrium frequency with maximizing the number of heterozygotes I get, it also means that I maximize the number of horrible genotypes I get, either the PP or the QQ. Let's take a look. So right now we have S greater than T. So we're going to do the same thing, only since S and T are negative now, we're going to say S equals negative 0.4, T equals negative 0.2. So notice that should make my P hat be the same of 0.33. So my 3 points where delta P is going to be 0, will be at all Q's, all P's, and this time again at 0.33. So where will my fitness values be smallest? Since S has the greatest negative value, when my P's are fixed, I'm going to have some low value here. T is also negative, but it's only half as bad as my S value, so that means it's much better to be an A2 individual than it is to be an A1 individual. You're still going to have twice as many kids. So that means the fitness, if I have only A2 individuals, is going to be higher than the fitness if I have only A1 individuals. And that means then that my highest fitness is going to be at 0.33, and remember, the graph is now a frowny face. So what it shows is that there's more area on this graph, all of this portion, where Sisyphus is going to push his boulder uphill towards a frequency of p equals 0.33. So our graph is going to be just the opposite again, and we'll see this scenario. So now what this tells us is we know exactly where we're going to end up again. We are not going to fix either P or Q, but we're going to end up at an equilibrium, and we're not going to end up at an equilibrium of 0.5 because it's much better to be a QQ individual or have two A2 alleles than it is to be a homozygote for the A1 allele. So because it's much better to be this genotype, QQ, rather than PP, we're willing to not have the optimal number of heterozygotes because we really don't want these guys at all. We just want to bash them back as hard as we can. But we can't get rid of all of the P alleles because then we'd never be able to make a heterozygote. But by maintaining some P alleles in the system, we can still have heterozygotes, who are the best genotype, and we can have some QQ or A2 homozygotes, and we're willing to accept them because they are not as bad as the A1 P squared individuals. Now you can probably guess that as these two values get closer and closer, we tend to push ourselves closer towards being at an equilibrium of 0.5. Okay, so that is the extent of what we have for looking at selection for homozygotes and selection for heterozygotes. We only have one example left, which is when we have to look at additive effects, and after that one we'll do an example problem as well.